Good morning, everybody. This is Mark Richardson with Vibrant Technology, and I welcome you to our November webinar. Today, we are going to be looking at a new method for doing impact testing, and we have named it the Slinky Impact Testing. I'm joined by my father, Mark Richardson Sr., who's going to be walking us through the webinar today. Before we get started, just a couple items. If you have questions during the webinar, there is a questions dialog box over in your GoToWebinar panel. If you just click on that, it'll pull up a dialog box and you can type in your questions. And at the tail end of our webinar, we hopefully will have some time to answer those questions. Additionally, if you have some questions that come up after the webinar, you can always email us at webinar@vibetech.com, and we can get those answers back to you via email. Or if you if you have any additional support questions, you can always just call into our support line as well at the VibeTech headquarters. What else? We are recording this webinar, so we will post this out to our YouTube site usually about 3 or 4 days after the webinar, so you can go back and review it if there's anything you missed during the webinar. All the attendees are in mute right now, and we'll leave it that way. We got quite a few attendees joining us, so if you do have questions, go ahead and type them in. That'll be the best way to get your questions answered. With that, I'll hand it over. Dad, if you want to take it over, and I believe we are looking at your screen right now.
Okay, thank you, Mark. And boy, we got a lot of material to cover today. Hopefully we can get through it all. We got some brand new ideas to introduce that are being implemented in MEscope as we speak. But I have breadboarded this new algorithm for Slinky Impact Testing using the scripting and hotkeys in MEscope and the math functions. So a little bit like MATLAB, if some of you are used to breadboarding your ideas there. We can do many of these things in MEscope also. So let's get started. I want to go through a few slides with you first, just to review what we did previously. Well, we'll get to that. Let's just talk about the different ways to test a machine or a structure. And if we're going to talk about mode shapes, and that's what we want to get to today, is getting some modal parameters, frequency, damping, mode shape from a set of experimental data. We need to talk about something called an FRF matrix. FRF, of course, is a frequency response function. It's the best measurement to make. It's not the only one that we can make and get mode shapes, but it's the ideal case where we measure the force, we measure the response, and there's two ways we can do a test. Here's the first one, a roving response test. So typically we do this with a shaker. The shaker is attached to the machine or the structure at one point in a direction. We call that a DOF, a degree of freedom or a point in direction. And then we rove the sensor around. The sensor is typically an accelerometer, but it can be any type of a sensor that measures response motion. The laser vibrometer is the one that comes to mind, or a photonic sensor. Those are non-contacting, sometimes very useful when we can attach accelerometers to the surface. So we're going to measure the surface vibration. We call that an ODS when we put a cursor in that data. What we're really measuring is the overall response of the structure. And here we see a picture of an FRF matrix. Now, to get mode shapes from a set of FRFs, we typically measure a row or column of this matrix. So in a roving response test, we are measuring a column. And we'll keep coming back to this, but those are the FRFs that we calculate from our input and response sensor data. So a roving response impact test would be similar, except we don't use the shaker. We impact the structure at the same point in the same direction and rove the accelerometer if we're using accelerometer, or we'll look at the Slinky test here in a minute, the transmissibility test where we have two accelerometers. That is another example of a roving response impact test. Okay, so here is a slide of a roving accelerometer test. We talked about this back in our September webinar, so if you go and review that YouTube video, there's some more details about that. So I'm going to go through this rather quickly. This depicts a roving accelerometer test where I impact over at a DOF of this plate. It doesn't matter where I impact as long as I do a repeatable test. I hit at the same point in the same direction. Last month we talked about measuring repeatability using what we call an ODS correlation. So that's another method in MEscope you can use to do this type of test and move the accelerometer from one point to the next. And of course, if it's a triaxial accelerometer, then you're going to measure 3D motion of the machine or structure as you move it. So that's an advantage of doing a roving response test. Here is the transmissibility chain measurement process. This requires a two-channel analyzer, and so we're simultaneously measuring the response of two accelerometers, or other sensors. We're not measuring the force in this case. And as I said, in September we went through this whole process of measuring transmissibilities. They are different than FRFs. They're the ratio of the two accelerometer signals computed in a frequency domain. So we'll take a look at that in a minute. And we're going to review the project that we used in September where we call it a Slinky test. And it just requires less movement of your sensors, your accelerometers. And MEscope can be all set up to acquire this type of data in what we call multiple measurement sets, where one of the accelerometers is called an input and the other is called an output, and we compute the transmissibilities and then post-process them. So we're going to go through that here in a minute. Here's the other type of a test that's very common with an impact hammer, called a roving impact test. So again, back to a picture of the FRF matrix. Now this is just a 5x5, but if I'm testing, 30 points, 50 points, 100 points, then this is a matrix of all the possible measurements I can make on a structure. Well, I don't need to make all those measurements. That's way too much work. But I do need, in order to get mode shapes, I need to measure a row, and it can be any row. The row is defined by where I attach the response sensor, let's say the accelerometer. So wherever I attach the accelerometer, that defines which row of this matrix of possible FRFs are going to be calculated from the impact force and the response caused by that force. So here's a depiction of a roving impact test, very commonly done, where now I interchange the accelerometer. It's fixed now, and it can be anywhere on the structure, and I go along and impact at various points in different directions. In this case, we're just indicating the vertical direction. Okay, so here's what we're going to talk about today, and this is a Slinky impact test. So rather than measuring a row or column of FRFs, we're going to measure in a very unique way you can see these are the off-diagonal elements. Now, the diagonal elements are the ones down the diagonal. That's where the impact or the input is the same as the output or the response. But here we don't ever measure a diagonal element. We measure these are off-diagonal elements. So this one over here would be 0.1 and 0.2. The one below it is 0.1 and 0.3. Then we move over here and we measure between 0.2 and 0.3, then 0.3 and 0.4, and finally 0.4 and 0.5. So that's a different way to make the measurements. The interesting thing about this, and we'll see it in a minute, is that we can use a wireless two-channel analyzer. So we're gonna use that here in a second. This is a device made by a company called GTI Spindle, and it's a rather new wireless device, and it's a two-channel device. So in order to make these cross-channel measurements, we need to have a two-channel, either a portable data collector wired to a hammer and an accelerometer, or in this case, we're going to demonstrate the use of the GTI with a hammer and a wireless accelerometer, and the signal is wirelessly going to the computer, my computer here, and we'll show you an impact on a structure. Now, it's a little exaggerated. Let me come back to this. Let me go to the picture, and we don't test large things around here. We've got small things, and our Jim Beam is our favorite test article. So what you're looking at here is the GTI wireless accelerometer, and it's simply attached with some sticky putty to the top of this Jim Beam, and then the hammer is got a wire coming out of it, but the wire is going into the side of this wireless accelerometer and transmitter device. So two channels of data are being simultaneously acquired in this device, transmitted through the air to the two sound channels in my computer, and then MEscope is picking up that data and post-processing it. So let's go ahead and try that. I've got a helper here who's going to do the impact, but we're going to bring up MEscope here, and I'm going to open up the GTI Impact project. Now, this project only has an acquisition window in it, so you can see the acquisition window. Let me make this even larger, and we'll fill the whole screen here with the window. Now, if you're not familiar with the acquisition window, you're looking at some graphics over here plus some setup over here on the right. The top two graphics are the acceleration response of the GTI and the hammer impulse signal. So those are the two signals coming in through the two channels of my computer, the two sound channels. Below down here is a FRF and its coherence overlaid on it. So coherence is a good thing to measure when we make FRF measurements, especially with an impact hammer, and we do any sort of averaging. So my measurement is set up here. I'm going to measure an FRF, or a transfer function, coherence. I'm only going to display some of the lower frequencies here so we can see, even though this device will go way out to a much higher frequency range, we're only going to look up to a couple of kilohertz here. So we've limited our display to 12% of the actual acquired data. And here is the setup for the front end. It's very simple. This is the number of samples that we're gathering from the front end, 4,000 samples, and you can see that the maximum frequency here, what we call F max, is at 22,000 hertz. So that's where the sound card will sample the data for us. Okay, we're ready to go. I'm going to connect this to the GTI. So these are all the different front ends that we can connect MEscope up to. So this is our VES 700 option to MEscope, and this allows us to do live data acquisition from a number of different third-party hardware front ends. So this is just one of them. Okay, so we're connecting up, and now the software is ready to acquire data. And I'm going to go up here and tell it to start. I'm going to push this little green button up here. This is a green go button, if you will, and it should come up. Now we've set up the triggering and so forth. There you can see my colleague is going ahead and impacting. Let me put the, maybe we can go back here. Nope, wrong one. Put that down and go back to our, where's our camera? Looks like I might have closed it.
That's good meeting, sorry.
No, that's not it. Let's try this one. Okay, I must have closed the camera. So here we are, we're back. Go ahead and impact it, and we can okay, we're going to start MEscope. Camera, where are you? Okay, here we go. So we just did 2 averages and pretty good coherence, very nice impulse response. So we can check all of the signals coming in to MEscope. It's important to check the time waveforms first, and then you can see we got a little pre-trigger delay in here. We've got the triggering set up down here in this spreadsheet. I'll zoom in there a little bit so you can see that. We're triggering on the second channel, which is the force channel, and with a little bit of pre-trigger delay so that we grab the entire impulse. That's a very nice signal. And we got a pretty good measurement off the Jim beam. Now Jim beam has very high frequency resonances in it, so this device is really designed more for machinery, let's say a piping system in a plant or a heavy machine where the G levels would be much less. So if we put this device out on the end of the Jim beam, it would not only mass load the Jim beam, but its dynamic range would be exceeded, and we'd see an overload of the time records. Anyway, let's move on. Thanks, Pat. Let me shut this down and let's go open up. I'm going to take you through the Slinky transmissibility test very quickly, and we had that all set up a couple of months ago. Just a little review of the transmissibility test, and the advantage of this is that we can use the same device that you just saw in action with 2 accelerometers. Rather than the hammer and the accelerometer, we can use 2 accels. They'd have to be uniacs since it's only a 2-channel device, and we can do a transmissibility test with either impact or on a running machine or on a piping system. This wireless device would be very handy for a number of different test environments. Okay, so I've got some hotkeys up here. I'm going to push the hotkeys. Those are going to run some scripts. And here's a script coming up, and it's saying animated frequency-based ODSs. Drag the cursor to display a different ODS. So this is how we started, and this is the basic capabilities of MEscope. If I make any type of measurements, single row or single column the FRF matrix of possible measurements that I can calculate. This is what MEscope is good at, looking at a spatial distribution of a resonance. So that's the first hotkey. I'm going to press the second hotkey, and now I'm going to simulate some excitation of this flat plate. And what's it telling me here? It's saying that transmissibilities will be calculated from data that is acquired 2 channels at a time from the random responses below. So here's what the random responses below are down here. So what we've done is excited this flat plate using its mode shapes that we were just looking at. Actually, we didn't curve fit the FRS. We were looking at ODS. ODS is in animation, but the ODS is basically a contribution due to the resonances or the mode shapes. And on a lightly damped structure like this, you're going to see the ODS and the mode shape pretty much look the same. So let's go ahead and start taking the data. So you can see the acquisition window up here is acquiring transmissibilities, and they're being displayed down here with the color. And you can see on the model here, the acquisition window is connected to the model, and it's showing the input and output accelerometers as data is being acquired from them. We're doing some averaging down here of the responses. So this is a response-only transmissibility test. As I said, it could be a running machine, it could be a piping system in a plant, it could be anything where we don't need to measure the forces. And a car running around a track, we can't measure the forces, they're distributed. And the only thing that's required here with these transmissibilities is that the force is applied at the same point, same direction. We can't measure it. We call that steady state. Modes are only defined for a steady state system where the forces are being applied in at the same point in the same directions. A car running, there's all sorts of forces from the motor and the ground and so forth. So there's a lot of inputs, but the levels can go up and down because the transmissibility, remember, is a ratio of 2 accelerations. So if, again, a linear system, if the responses move up and down, the transmissibilities are going to account for that. So you can see some of these don't look like FRFs at all. They're very strange looking because it's a ratio of 2 accelerometers. Again, the GTI device would be ideal for doing this in a wireless environment. Okay, let's go to the next one, and here it is. So we're going to post-process these transmissibilities, and we're going to do what's called a seeding. So we got this transmissibilities on the left, and they're going to be seeded with the cross spectrum to yield a single reference set of cross spectra on the right. Now remember, when we looked at the FRF matrix, a single reference could either be a column or a row of possible measurements. The same goes for cross spectra. If we're going to look for mode shapes by curve fitting cross spectra, which we can do, or simply animating with a cursor in the cross spectra to get the ODS, we need a single reference set. So now we're converting this multiple reference set of transmissibilities into, we're seeding it with a set of cross spectra, actually a single cross spectrum. And then we went through this in September. So you'll have to go back and look at the details of that in that video. And then the final one here is that we can do a comparison animation between the original mode shapes and the cursor position in the cross-spectrum data. So there's a lot of other details to talk about here, but you can see that we're sweeping through the mode shapes that were used to simulate the random response. That's our MIMO calculation, multiple input, multiple output, part of our advanced signal processing in MEscope. And you can see that we went a round trip here and recovered some ODSs. All right, let's move on to what we are supposed to be talking about here today, and that is Slinky Impact. So let's go back for a minute. I'll open up the Slinky Impact project. Again, this is a project with some hotkeys and some scripting in it, which will take us through a number of steps in MEscope, using MEscope commands. So a script is simply a spreadsheet with some MEscope commands in it. And you can see I got a whole bunch of hotkeys up here. We're going to use them all. So let's go back here for a minute and review what we're going to do here. We're going to simulate a Slinky Impact test. And we're not measuring a row or column, so we're not going to get a single reference set of data. But we're going to go ahead and curve fit these FRFs, these off-diagonal measurements that are very easy to make with a 2-channel wireless device or a portable collector and you know, wires to a hammer and an accelerometer, and then we're going to post-process the curve fit results. So this is a little different. Now we're going to take advantage of a property of what we call residues and mode shapes. They're related to one another. Now when we curve fit an FRF, the numerator or the strength of a resonance is called a residue. We're not going to get into much of the math today, but what I want to show you here is that a residue carries the same degrees of freedom as the FRF that it was measured from. So just look at the math here for a second. We'll get through this painful part as quickly as we can, but a vector of residues, and we call this a residue mode shape in MEscope, is simply an assembly of the residues that I get by curve fitting some FRFs. Now in this case, we're not getting residues with a single reference in them. This is MEscope notation where the first number is the DOF of the, in this case, just the point number of the roving, followed by a colon, followed by the DOF of the reference. So here you can just see in this little example, we've got 2 different references and kind of a mix-up of the roving, but these correspond to these 3 measurements right here that we can make with an impact hammer and an accelerometer. So we're going to make those 3 measurements. Over here, we need a mode shape that's got, you know, components in it that are 1, 2, and 3. And those would be degrees of freedom 1, 2, and 3. That's what we're trying to get out of this data. Well, here's the relationship between residues and mode shapes. And this is as much math as you need to know, that a residue between DOF 1 and 2 is really the product of the mode shape component at 1 times the mode shape component at 2, and so on here. Point 1 and 3 is 1 and 3 multiplied together, and so forth. So what we do after we've curve fit this Slinky FRF data is we can go in and take the first 3 measurements. Here's 1, 2, 1, 3, and 2, 3. Do a little math. These are complex values, so we got magnitude and phase, but MEscope can handle all that, and we get a mode shape component of 1. Now that we have 1, we can go to residue 1, 2 and divide by that, and now we get mode shape component 2, and so on. We get 3 from 2 and 4 from 3. That's the whole idea. So pretty simple math. MEscope can do these kind of things. And let's go ahead and look at a simulated Slinky impact test. So here's some impacts here in a window, and what we're going to do is build a whole data block full of impact signals. You can see there's actually 3 of them here. And so we're going to do some averaging of the data. So what I've done here with this first hotkey is basically just filled up a data block with the same impact signal, except there's 3 of them. And we're going to use MEscope to, first we're going to take these impacts and compute the response of the flat plate to the impacts. Then we're going to post-process the impact and the response in an acquisition window as if we're simulating a real impact test. Now in real life the impacts wouldn't all be the same, but it doesn't matter because this is kind of another input-output model that we're going to get the outputs due to the impacts. Now, we could have randomized the impacts, but we're using the same ones here. So now the MIMO calculations are going on here in the background, and we're computing the response of the flat plate to 3 impacts at each of the points. And we'll see here in a minute when we post-process this data how the Slinky impact test actually proceeds. Taking a minute here to rattle through all 30 points. There's 30 points on the flat plate, and we're computing responses to all 30 points due to the impact at a neighboring point, and you'll see what I mean by that in a minute. So here are the responses, and let's just kind of look at several of them here together. So this is a cascade plot, what we call cascade in MEscope, and you can see that certain points on the structure respond a whole lot better to those impacts than other points. But that's all in the dynamics, and these were computed by using the mode shapes, the 5 mode shapes of the flat plate. We'll look at those in a minute here too. So I'm going to go ahead and now we're going to pair up the forces with the responses. So all this is going to do here is kind of put things together in one data block so that the ACK window, our acquisition window, can post-process the force and response data, just like we demonstrated with the GTI wireless device. Okay, so there we are, and this is all of them. Let's just look at a few of them here. So this is pairing up the inputs and the outputs, or the forces and the impacts together in a single data block, and then we're going to feed this data in and post-process it in our acquisition window and compute FRFs. Now we're going to curve fit the FRFs, then we're going to sort the residues, and we'll look at the results. So here the next one is acquire the data. So now we're going to set up a acquisition window similar to the way we did it with the transmissibilities, and it's going to walk through well, let's see, what's it going to do here? Okay, it says press the F5 and X6 keys to display Slinky output over input pairs for each measurement set. Well, there's a pair for each measurement set. This is something else that we have in MEscope. When we're doing these kind of tests, we can set the whole test up with the degrees of freedom, the input, the output, how we want to make the measurements. That all happens inside the acquisition window. And so Slinky post-processing of the measurement sets will begin by pressing the next hotkey. So we're simply going to make FRF measurements here. And again, MEscope is set up with scripting, so it's going to rattle through all the 30 measurement sets. It's got a bunch of measurement sets here, and I think we might have a problem because we're still connected to the wireless front end. So let me say none here, and let's start this over again. See if we can get this thing going. Okay. You can see the first case over here is we're going to impact with a hammer at point 1. We're going to measure response at point 2. Pat, I need your help to turn off the wireless. Yeah, it's interfering here with. How do I do that? All right, let's see if we can make a measurement here.
Did you want to make a measurement using wireless?
No, yes. No. This is all simulated here. It's going to walk through this Slinky test here. Simulated. No, it's not running.
So we're currently connected. Let's go to the aqueduct.
It's supposed to do that automatically. Data block. Force and responses. Okay, it's done something here. Let's see if it's going to connect and start the test. It still seems to be not connecting.
Let's touch the aqueduct. The front end is currently ready. If you hit go, it should acquire.
No, they're supposed to do it with the script. Oh, here's where we are. I'm not paying attention to the message. This is what we're looking at here. So, operator error, sorry. This, as I push the F6 key, you can see how the Slinky test is proceeding. Now, we haven't started it yet automatically. This is just allowing me to show you that we're going to, let's just stop here at this one. So let's say I've got the accelerometer here at this point, and this is the input at this point. So then I'm going to do a Slinky. I'm going to move the accelerometer to the next point and impact again. And so now I leave the accelerometer there, I impact over here, and now I move the accelerometer and impact at the same point. So you can see the Slinky impacting is very simple. I don't need to change anything except in my acquisition window, each of these measurement sets has been defined with the correct point and direction on the model. And so this is just walking through as I push the key on the keyboard here, going through each of those. Now if I go to the next button, remember it told me to, here, let me go back and do this. I wasn't reading the message that came up. So it said press the keys to display the measurement sets. Each measurement set. Slinky processing will begin by pressing the next hotkey. So here we go. So now the scripting in MEscope is going to do it all for us. Let me make this a little larger here after we get connected. Now what you're going to see going on here is it's the acquisition window is connected to the data block down here on the lower left, and it's doing 3 averages. It's actually averaging, you can see the cursor moving along there, taking several thousand samples of data out of the data block, calculating FRF and coherence. And then as it computes each one, it's accumulating them down in here into the lower right data block where you can see each measurement and its coherence overlaid being accumulated down there. So this is all happening as I speak. You can see the scripting is simply simulating the Slinky test. By the red arrow is the hammer location, the blue arrow is the accelerometer location. Now these are FRFs, so we'll be able to curve fit them, and then we're going to sort the residues using some of that math that I showed you earlier. And then we're going to compare the mode shapes with the original mode shapes that were used to set up this whole simulation. Okay, Slinky FRFs have been calculated. Press the next hotkey to curve fit the FRFs and sort the residue mode shapes. So we're going to go ahead and press the next key, which is this one. And let's see what we're going to get here. Okay, so the first thing it's doing is removing the coherence from the data block. We could leave it in there. The curve fitting will ignore the coherence, but this scripting removed it, curve fit the FRFs, and the Slinky residue mode shapes are saved over here in this table of shapes. So here's what we have from the Slinky test. Now these are not, we can't display these because if you look here at the references, those are the same as the references of the FRF. So we got 2Z, 1Z, 3Z, 1Z, 3Z, 2Z. So this is what we call a multiple reference set of data, but it's not even, it's worse than that. Every residue has a different reference. So we cannot use this data as it is. We need to sort it. And here's the hotkey that's going to sort the residues and give us a set of mode shapes that we can work with. So here it is, it's rattling through and it's building up another shape table of mode shape components. Let's call them mode shapes because that's what the math told us we would get. And you can see they've been labeled as OMA mode shapes. They're no longer residues. They're not unit modal mass mode shapes. We're not going to go into all those details here today, but these mode shapes, you can see they got magnitude and phase in them. That's what we got from the using the formula that I showed you earlier, where we took 1, 2, and 3. We took those residues and multiplied, divided, took the square root. Now we had sort of a seed. We had the first component, and then we were able to compute the rest of the components. So let's go through here and animate these. We're going to compare the mode shapes with that we got out of this Slinky test. Okay, Slinky test mode shape on left is compared with the UMM mode shape on right that correlates closest with it. So this is a feature of our comparison display that we often use. We compare ODSs with mode shapes. We compare FEA mode shapes with experimental. And up here, so here what we're comparing is the result of the Slinky test on the left with an animated shape of the UMM mode shapes that we started with. That's what we call a modal model, and we synthesized random responses, not random, but impulse responses using the modal model, and then we went and post-processed and got the FRFs. So we did all that. What these two indicators are showing us here is the first one is called modal assurance criterion, and it's equal to 1. And as we sweep through these various mode shapes, let me click back here, there's the first mode, torsional mode of the plate, and it went to the first bending mode on the long direction, and then the bending in the stiff direction, exactly what we expect to see. This is data coming off of some real FRF measurements. And so the MAC value is saying these are the same mode shapes. Now they don't look like the same mode shapes. Well, they kind of do, but you can see there's quite a phase difference between them. The second indicator here is called the shape difference indicator. And it's telling us that these new mode shapes we got are scaled differently than the UMM mode shapes. They have different numbers in them, basically. Even though they're collinear, the MAC value says, hey, they're the same shape, they lay along the same straight line, they're different by a complex scale factor. And why am I saying that? Because they're animating so differently. Let's go here to the last hotkey, and that is the one that's going to scale the OMA mode shapes, what we call OMA mode shapes, using the UMM mode shapes. So here it says the Slinky test mode shapes are scaled differently than the UMM mode shapes. And this is what we saw from the diagram, or from the SDI calculation. It computes the difference. The MAC computes the collinearity. That's the difference between those two indicators. So press continue to scale the Slinky mode shapes using the UMM mode shapes. So we're going to go ahead and do that, but let's just take a look here. These are the SDI bars between the UMM mode shapes and the Slinky mode shapes. Let me make this a little larger so we can see there's the scaling. So on one side of this bar chart are the UMM mode shapes, the other side are the Slinky mode shapes, and they're only 50% alike in value. Now if I go down here and press the continue button, which is down here on the progress bar, bingo, the Slinky mode shapes have now been rescaled, and so when I compare the shape difference indicator between the two sets of mode shapes, they are in fact, they've been rescaled so that now UMM mode shapes are typically gotten out of an FEA model, so I can take any kind of experimental data, however I get it, ODS data, Slinky test data, residue data, and I can scale it to UMM using this command in MEscope. So let's go back here and do the animation now, since we've rescaled the Slinky mode shapes, and you can see that as we sweep through, the two indicators are both indicating that we've got the identical shapes, and even though we got the ones on the left by the Slinky tests and the ones on the right were what we started with, we've ended up with the same result. Mark, that's all I have for this webinar. Do we have any questions?
We don't have any questions at this point. I ran into a few little difficulties on my end, but hopefully it was isolated on my end. So, but I do not see any questions at this time. If you have some questions, by all means, you
we
can
either have a
email
very
us.
good class or we put them all to sleep. So that's all I can conclude from this.
It was a lot to digest, and again, we are recording this, so we'll have this posted out to our YouTube page in a few days. Dad, why don't you give a little introduction for what we're going to do in December?
In December, we're going to try to get it in early before the Christmas holidays so that you can have a chance to come and attend. We're going to handle the subject of curve fitting FEA mode shapes to experimental data. Now, this is essentially a command that we have in MEscope that is called shape expansion. So I'm going to go through the details and explain to you how we can take analytical mode shapes, normally called normal modes, no damping in the FEA model, just mass and stiffness. Take a set of analytical mode shapes, curve fit them to some experimental data. The advantage of doing that is the experimental data includes all the boundary conditions, all the properties of whatever is causing a machine or structure to vibrate are included in the experimental data. We're actually measuring the true response of it. When we curve fit the FEA mode shapes to that ODS data, we are applying a fundamental property of any resonant vibration, and that is that the ODS data that we measure on a machine or a structure is contributed to by all of the mode shapes of the resonances. Another way to say that is that all resonances are excited at all frequencies. So we'll look at that both in a time domain, the frequency domain, and we'll talk about how useful that can be in our next webinar. So with that, I guess we'll wrap up, Mark. And
yeah, I just want to let you know that webinar is going to take place on December 21st. So we will get that out in our newsletter, which will probably head out first part of next week. And you can go ahead and get registered through the link that's in the newsletter.
All right.
All righty.
That's it for
Everybody
today.
have a good one.
All right.
Thank you.
Bye.
Bye-bye.
Oh boy. Sitting there trying to get it to do something. It was telling me,